Good evening. We're here to talk to you tonight about a problem plaguing our agricultural industry. The demand requirements are increasing on the average farmer faster than the supply chain can handle. We're proposing a solution to this problem through monitoring of atmospheric and soil conditions to give the farmers real-time data to make adjustments and decisions to increase crop yields. The design requirements of the project are the ability to gather atmospheric and soil data, the ability to plant, irrigate, and fertilize when necessary, and all components of the project must be able to communicate with each other. We've designed three components: a ground drone, designed by Gerard Gartner, an aerial drone designed by Cal Ackerson, and a central hub drone designed by Mark Shamlin. The ground drone had a list of requirements. One, it must be self-propelled. It must have the ability to deploy two probes. It must be able to identify soil types, read pH levels, read soil temperature, and soil nutrient levels. The second probe would be used to gather moisture levels of the soil. Here's a 3D rendering of the ground drone. It's driven by two electric motors. The battery box is mounted under the chassis central to the vehicle to prevent tip overs. And it has two probes, one located on each end of the vehicle. There's a compartment on the top to store the electronic devices. Here we have the drive circuit to power the motors. We're using two gear-driven two electric motors with gearboxes. We're also using a ultrasonic sensor to detect distance from objects, with a threshold set in the programming to 8 inches. Once the vehicle gets within 8 inches of another object, the motors disengage. When the distance of 8 inches becomes greater than 8 inches, the motors re-engage. Here we have a demo of the programming working. You can see on the gearboxes the RPMs the motors are turning currently. As we drop below the threshold of 8 inches, the RPMs go to 0. We come above the threshold of 8 inches, the motors re-engage. Here's the circuit for the probes on the drone. It consists of the Adreno controller and two servo motors. It is designed so when we deploy one probe, we deploy both probes. It's single control aspect. Here we have a demo of the program running. Here we're engaging the probes to go on the ground, and the servo motor is going to rotate 180 degrees. When the signal gets cut, they rotate backwards 180 degrees back to 0. Here's a combined circuit with the drive motors and the servo motors. There is a delay programmed in to prevent the drive motors from engaging while the probes are still deployed. The flowchart for the ground drone: when we start the drone up, it initializes and connects to the main hub. It waits for user-defined parameters. It gives the command for the probes to be up. We then are going to move to the probe locations. We check the probes are up. If the probes are not up, we give the command for the probes to go up, reinitiate, move to the probe location. The probes are detected as being up. We go up and we engage the motors. First thing it checks is there any object closer than 8 inches to it. If the answer is yes, it stops all movement. If the answer is no, the drone proceeds to move to the probe location. When it gets to the probe location, the motor stopped. If the motor is not stopped, the stop command is given. If the motors are stopped, we deploy the probes. The probes gather their data. Once we have gathered the data is then sent to the main hub. At this point, I'll be handing you over to Cal Ackerson so he can tell you the details about the aerial drone he designed.
Hello, my name is Cal. I have developed the aerial drone, nicknamed the Little Mermaid, for the 11th hour. With the follow-on requirements set as self-propelled, integrated with LiDAR, GPS, multispectral imaging, atmospheric data collection, air quality, and communication relay. I will go and expand on these later in this presentation. Here we have the mechanical display CAD of the aerial drone. There have been slight modifications to the initial design with the integration of the atmospheric data sensors, GPS, solar panel, and LiDAR down at the bottom of the drone. The solar panel allows for longer flight times. Then we have our propellers on the left and right side, or front and back, however you want to look at it, with a ring around each blade, each propeller, to allow for protection of the blades in case of any mid-air collision with a obstacle or another drone, as well as any crashes that may occur. Next, we have the temperature LCD circuitry. This is in relation to the atmospheric data collection. Other atmospherics that we would collect are temperature, pressure, as well as air quality. So Over on the right side, we have the code. We have the liquid crystal library, which allows for the Arduino and the LCD screen to work in conjunction. We have the LCD set up to 12 and 11 pin, as well as the 5, 4, and 3, and 2 pins. Then we have the sensing pin for the temperature sensor set at analog 0. Next, we set up the readings of the actual LCD. It will print current temp and then relay or jump down to the loop, where it will collect from the sensor, convert it into a readable format for the temperature, and present it with current temperature at Fahrenheit readings. I will expand, and you'll see the actual temperature gauge in work later in this presentation. Next, we have the flight controller. This is a setup with only 2 engines, 2 DC motors. The actual drone will have 4, 1 motor to control each wing or each propeller, so that way we can allow for precise flight and guidance of the actual drone. We integrate it with the proximity sensor to control whether or not the engines are running in forward or reverse, left or right. On the right side, we have the code with the motor pins for the first motor set to 5 and 6, motor 2 or set to 2 and 4, with the ultrasonic sensor set to 11 and 10. We have the initial setup of the motors, as well as an LED indicator to relay on the proximity of the drone to an obstacle or another drone flying. Next, we are in the loop. We have the initial setup of the sensor, as well as an if-else statement to the proximity in inches, 20 inches. We'll relay a digital write to the LED to indicate red at a high, so they will light up red. Next, it will cut all power to the engines, which will stop the aerial drone from flying and avoid the obstacle. Next is the within 60 inches, changing the LED to yellow and slowing or reversing the aerial drone to avoid the obstacle. Anything else, the LED will be in green with a forward flight path. Here we have the code with the LED green, changing the distance to what resulted in yellow, changing again results the LED in red, and the engines cutting off. Next, we change it back to yellow. We see the LED change in correspondence, and then again back to green. Next, we will go into the temperature collection. You see the sensor change in relation to the temperature presented on the LCD. Here we have the flowchart with the initial start and the initializing of the console, takeoff of the drone, the initialization of the atmospheric data collection, as well as the LiDAR and GPS systems turning on and beginning its collect, and mapping of the farm. Surveys the farm, computes on whether or not the mission is complete. Since we just began mapping the farm, it'll be a no. LiDAR and GPS data collection, proceeding, integrating the atmospherics, the LiDAR and GPS data all into one system, and then analyzing through on the onboard system to determine, based off the atmospherics, the LiDAR and the GPS, on whether or not planting or irrigation is required at that known location. If no, it continues mapping the farm to find a likely or quality location for planting or irrigation. If it finds one, it says yes. It begins transmitting the data to the terrestrial drones through a communication relay to the central hub. Communications include the environmental conditions and recommended actions and the mission status of the aerial drone or of the terrestrial planting and irrigation. If it communication relay works, the data transmission will be determined on whether or not it's a successful transmission. If not, it tries to retransmit the data until successful. Once the data is successfully transmitted, the aerial drone will continue to survey the farm for any additional locations for planting and irrigation. Let's say it's now completed the mission or the mapping of the farm. It says yes. It will then return to base for next day, next turn. I will now turn it over to our next team member, and they will discuss the central hub.
Hi, my name is Mark Chamberlain, and my drone was the crop conductor. The requirements for which were to gather data from the collection drones, detect what section of the farm it's in, adjust soil pH as needed, as well as raise soil moisture levels, and plant the seeds when conditions are optimal. Here we have the crop conductor drone design. In the green, we have the irrigation nozzles. The light blue stem up there is the comms antenna for communicating with the data collecting drones. We have a solar panel on top, and in the yellow towards the bottom there, we have the rake for tilling the soil. To the right of that, we have the underside of it, where it houses the 2 pH light adjustment valves, along with the seed release valve. Bottom left, we can see a cut open portion that has the boxes of the pH subtracted folder and the pH additive folder, as well as the sage green seed holder. Notice the ramps that funnel towards the valve. Finally, we have in the orange with the that has the electronics bay, and then the lilac here that has the irrigation container, which is then pumped out via these black irrigation pumps. Here's the crop conductor circuit. I have included my 3 seed and pH adjustment valve servos towards the left, as well as my motion components at the top with my steering servo and my forward and backwards hobby motor, as well as my DC motor here at the bottom as my irrigation pump. Notice how both the DC motor and the forward and backwards hobby motor need to be connected to the motor driver, while everything else was available to just hook straight up to the Arduino code. here's the fun part. So I created a class that basically had a constructor that set all of the parameters to 0, and then it was a class of getters and setters, where all the data collection bots would set the values that they get, and then my bot would then pull it with the getters. In the middle here we have my variables and constants. At the top we have my optimal ranges for all my components, which is what a user will input. We then have the current, soil, current, moisture, all that, which would then be set to our getters, which you see to the right in our gather data method. After that, we have all of our booleans to check if these parameters were like good to go. We then have our servo instantiated. We then have the servo pins getting called, as well as the DC motor pins and the hobby motor pins getting set. Finally, we have our motion constants, as well as our grid location, the current X, Y, Z grid location, as well as the steer straight and left and right, steer straight at 90, and then to left and right, we just add subtract 45 degrees. And then we have two booleans. One is it going down, like which way is it going down a row in the grid, and the other one is did it complete the grid. Finally, here we have a method for enter optimal conditions. It's basically just prompts the user to enter in their conditions, and it also double checks that it makes sure that the minimum is actually lesser than the maximum they enter. Otherwise, it will prompt them to re-input. Next, we have the optimal conditions method, where it just checks that the getters that pulled from the data collection hub, or the data hub class, it will check that against the range that the user inputted. For soil pH, we were actually able to adjust it, which I had set to either plus 0.5 way to add pH or minus 0.5 way to subtract pH. And then moisture, we can actually add moisture to the soil, but we cannot subtract it. So only if it was less than the parameters, we would be able to add it at intervals of 0.5. Otherwise, it would do nothing. And then all the other ones, it's unfortunately just nature, and you just have to move on if you can't. At the very end of this method, there's a boolean that checks if all of these were within the optimal range, then it will plant the seeds. If it was not, then it will not plant the seeds. Let's see. Finally, number 3, we have my steering motion method, which is just my forward, backwards, am I moving? My stop movement, my steering left, right, and then making sure I'm going straight. We use those in our move to method, which basically gets what section we're in, and then actually snakes us through the grid. So it will start off in 0, 0, and then it will then go up to 1, 0, 2, 0, 3, 0, etc. until it reaches 9, 0, where we'll then turn right into 9, 1, and then start going down the row for 8, 1, 7, 1, 6, 1, all the way to 0, 1, where we'll then go to the next row for 0, 2, 1, 2, 2, 2, etc., all the way until it reaches 9, 0, where it will print out a completed grid, and it will trigger the stop moving method, and then it will actually trigger this boolean to be true. Finally, we have what populates normally in Arduino code with the setup. We have the 0 begin to initialize console. We attach all our servos to respective pins. We then enter the optimal conditions, which again prompts the user to enter the conditions. Then we go into our loop, which double checks that the conditions are being met. And if they're all being met, then triggers the seeds. It opens the servo, delays it for enough time to trigger the seeds, closes it. If only one of them are not met, it will then say conditions are not ready. Move to the next location, and then it will then move to the move to method if the grid complete boolean is still false. And if it's at the very end, it will be true. All right, and here we will actually demo our code. So I will go ahead and start the simulation. The steering servo will trigger to 90, and then it will prompt me to input a minimum soil pH. I will start with 1, and then I will then go enable 1 to show that it will actually trigger a prompt. Make sure minimum is less than maximum. Fantastic. So starting at 1 and 2. Let's trigger the additive twice because it goes up by 0.5. Same with moisture. We'll just go for 1 and 2. And everything else, because the constructor is set to 0, since we are using a class that can actually not communicate through Tinkercad like you could in the real world, we have to just go based on constructors. So we'll also be setting everything to negative 1 and 1 for the rest of the movers. Giving the feedback, release this pH additive, triggers twice, and then we move to 1 up, and then we'll move to 2 and 0 after trigger C. And we'll do this all the way until it reaches 9 and 0. However, what if we wanted to not meet these conditions? So let's go ahead and clear this. Set this mission again. So soil pH is always going to reach it, so we'll just do 1 and 2 again. However, soil moisture, we can just go 0 and 1, so we can just kind of bypass that. Let's say soil temperature is too low. Say it's -2, -1, it will never reach that because the constructor is at 0. And then the rest, we can just put in any number we want. High for air pressure, for air moisture, it's also too high. And then we'll just say for air temperature, it's also too high. So none of these will trigger, but any one of these could just be off, and it would just not hit this boolean flag. Sorry for air temperature, let's go. There we go. Oh, giving feedback for all the inputs. So you see it'll give me the input for what it's not in the optimal range for, will not trigger the seed, and then we'll continue to move through. Here we have the flowchart for the crop conductor bot. I'll start, initialize the console, and touch servos, call and enter optimal conditions method. And this will then prompt the user to enter the range of optimal conditions. It'll print the user's input as feedback. Then we'll call the getters data hub class with the get data method. Then we'll call the optimal conditions method, which will then check if the soil pH is in range. If it's not, so then it will then check if it's greater or lesser. If it's lesser, we'll add pH. If it's greater, then it will subtract. And then we'll then loop back. Is it within range? Finally, it is yes. And soil moisture lower than the parameters. If it is yes, it will trigger the irrigation until it meets it. If it is no, or it finally is meeting it, it will actually move on to the soil temperature within the parameters. If yes is air pressure, if yes is air moisture, and if yes is air temperature all within the parameters, it will then finally trigger the seed servo opening. If any of those are no, including the soil temperature within the parameters, meaning that it started too high, then it will then go to it will then just be no, and it will go to is this the last section of the grid, and then it will then check is the box at the end of the row. If it is yes, we'll turn to the next row. If it's not, it will just continue to move down the row. Finally, we'll keep looping back through this by going all the way back to the call getters, the data class data for that section, and all the way until it's in the very last part of the grid. We'll then say stop movement and declare terminal and reach the end. Finally, we have the full swarm flowchart. Our swarm will start. The ground and aerial drones will start up. The ground drone will then gather soil data, while the aerial drone will gather atmospheric location data. Then they will both send this data to the data hub, where the crop conductor will then start. We'll then pull the data from the data hub, check if the conditions are optimal, and adjust it where it can. And then finally, if it can, we'll plant the seeds.